Thank you very much. I would first of all like to thank the Hellenic Air Force for organizing this conference, but also for promoting me Major General, because I wear a badge where I'm a Major General. I have to give that information back to Paris. Secondly, I would like to apologize for not being an air defense system specialist, as you've seen in my brief overview, but I will try to talk to you about the defense industry participation in research and development and implementation in air defense systems. I will give some general considerations on how we organize research and development in DGA. I will focus a little bit more on science and technology, which is a subset of this in the field of air defense, and give you a few more pragmatic examples of how this is implemented into real life. So first of all, this is the French organization. We have a white book on defense. The last one was published in 2013, clearing the way for strategical planning, I would say, from which we derive a military plan programming law that gives us a, I would say, budget view of a sliding window of 6 years, which is key in our business because you cannot run big major programs that last for years and years with only 1 or 2 years of vision. We also faced and still face very strong budget constraints. So part of the business in this military programming law was to see how we can conciliate budget cuts with the fulfillment of operational requirements, but also industry preservation, technological preparation of the future, because you don't want to only make your decisions based on operational considerations if you kill your industry. We in France spend about 1.5 billion euros every year in defense, science and technology. It's probably the first investor in Europe in this business, and this is very important. We spend about 3 billion euros every year in the development of new programs. So part of it is dedicated to subsidies to our national aerospace research center. ISL, for those who know, is a Franco-German bilateral research institute. Part of it is dedicated to dual research. I will come back to that later, especially in the space domain, where the Ministry of Defense contributes to the space effort in France. Of course, we have a strong convergence between interballistic missile and space launching vehicles. I will not elaborate on these technical prospective or technical operational studies. And a lot of this, so about more than 700 million euros, is dedicated to developing innovation and new technologies in industry. I will not bother you too much, hopefully, with the internal DGA organization. What is important that in terms of science and technology, or I would say governance, we have a strategic directorate that is in charge of the preparation of the future, combining the aspects I mentioned before: finance, industrial capabilities, operational capabilities. And this strategic directorate is responsible for publishing every 2 years the science and technology orientation document that sets the major priorities for our science and technology policy, I would say. Science technology programs actually themselves are then run, piloted, contracted, everything, by the operations directorate, the same that perform the acquisition programs. And we have a strong technical directorate, about 6,500 people, supporting the technical expertise to make this possible. Now a little focus on science and technology. This slide is to show that traditionally we had been spending a lot of money in, okay, maybe I will give a short explanation for those who are not familiar with this scale. This scale on the top is the so-called technology readiness level scale. So here, close to 1, you have really fundamental research on physics and stuff like that. And as you grow in maturity, you have here demonstrators and here full equipment ready for operation. So we have to address the whole continuum of this technology readiness level. The more you are in the right, of course, the more you are in the design and development phase of new equipment. Here you have very early stages of research. And traditionally, we had been focusing a lot on defense-specific research in what we call applied research contracts. But more and more, we estimate that defense-specific technologies and defense-specific equipment or components are very expensive, very costly in the long run. And it is our advantage to share as much technology with the civil world. So that's why we are focusing a lot more now also on dual technologies, and we've put in place financial incitations for SMEs and so on to whenever they innovate in innovation of dual interest. A few examples: exoskeleton. Of course, it's useful for the army guys, but it's also very useful in the industrial world. We have the sponsor that we say a flying buggy, low light level color cameras, functional paints that prevent rusting, that prevent anti-fire paints. These are of dual application. We organize science and technology in domains, of course. Recently we changed this segmentation to make it really industry-oriented. The purpose of science technology investment is to give a competitive advantage to your industry for the future. So really developing the skills within industry is what is at stake. So I will not come on each one of these domains. I will just highlight that for the specific domain I was asked to comment, air defense, actually there are many industries and many sectors that are involved. Now, what are our main orientations for science technology in the air domain? Did I skip one slide? Yeah. You will find this is the list of science technology air contributing areas, the first one. I will give you some priorities in the next slides. The common air technologies is not very self-explanatory. It's typically stealth technologies, common air technologies. All the first ones, air communication equipment network, intelligence surveillance, are more dedicated to airborne assets. Promotion of innovation is also involved in air science and technology. And information system and C2 are more for ground assets in this domain. The main issues, the main goals for us in this effort are the development of the future standards of the Rafale fighter aircraft, the future combat aircraft systems, including UAVs, for which we have performed cooperation work with Greece on the Neuron program, but this does not really belong to air defense, future standards of the Tiger helicopter. Now, what are these priorities? This is to give you a few examples. For air platforms or for combat aircraft, for intelligence and surveillance, our objectives are to develop detection, reconnaissance, and identification capabilities on very low altitude discrete targets. We have to do this not only in electromagnetic field, but also hyperspectral, infrared, and visible areas. And typical common technologies that are the objectives of science and technology innovation in common technologies are advanced radars, safety of operation of airborne computer systems, optronic components, hyperfrequency. You see a whole bunch of different domains. Now, to make this end up in a mature equipment, you have to organize, so I will not detail this slide, but we have what we call federative projects to make sure that all these little bricks of various research fields will eventually converge at the proper time into a real equipment. So we have to plan, I would say, the synchronization of all these different research activities to make sure that we are on schedule to launch a new program with limited risk. The whole purpose of this research activity is to make sure that when you launch a new program that will anyway be costly and lengthy, you limit the technological or industrial risks. So you see these federative projects combine several industrial S&T domains. They define a global set of studies to be consistent with operational needs. So we define roadmaps, and this is at this stage that we have the most, say, dialogue with the operators, the French Air Force, French Army and Navy, to make sure that the technological and industrial effort is oriented towards an operational gain. To end up, I will give you a few examples on how, in the end, this research and development turns into real projects and equipments in the field of air domain. The first one, it's a wide understanding of air domain. It's about the ballistic missile battle. We have financed and developed a demonstrator that is very helpful for us to understand the behavior of different architectures, different systems. So basically, you set up a set of inputs. What are the threats? Where are the launchers? What are the sites you want to protect? What are the resources you have for that? What are your political or military considerations? And with this, you run a simulator with different architectures, sensors, C2, effectors, and you can evaluate the behavior of your system, your architecture, depending on scenarios. You can have, it was mentioned earlier this morning, salvo firings, what are the fallout on different areas, and this has been very instructive for us to have, I would say, not a real simulation, but a very significant simulation on ballistic missile battle scenarios. And of course, the outcome of all this is that we are implementing a new version of our global air defense system called SCOA, and the results of this research and this demonstrator will be implemented in the next step of this incremental program. Another example is the radar development. Again, the idea of research and technology is to limit the risks of new programs. And we have now launched the development of new generation of radars, where the improvements that we are expecting are the improvement of detection and fire control capabilities with extension of surveillance and cueing range, smaller target detection. We are working in the S-band. We use active array scanning antenna, GAN technology, we have developed, or we are developing radars with fixed antennas and I would say electronic rotation for sea and land applications, and that are ballistic missile defense capable. This development can only be launched once a whole set of risks have been mitigated by previous studies. And so these developments are aiming at developing and building a Seafire 500 family, which is a 500 kilometers class naval radar, and the GF-1000, so 1,000 kilometers class ground radar. And of course, these activities are open to cooperation. One last example. The Aster 30 is an air defense missile. So I talked a bit about C2s, about sensors, now about effectors. I give one example in each. We launched last month the improvements of this program, what we called Aster 30 Block 1 New Technology, NT. Basically, the main changes that we switched from a KU band seeker to a KA band seeker. So there have been, again, research and technology studies performed to minimize the risk of developing a new seeker head in the KA band that will provide better accuracy and longer range, so that this new generation of Aster 30 will be more effective in against medium-range ballistic missiles up to 1,500 kilometers, ASBM threats, including, and this was one of the constraints, maneuvering ballistic missiles. So it has improved kill capability. It will be able to defend larger areas due to these capabilities. It also brings enhancements against conventional threats, what we call air-breathing targets, so typical cruise missiles or aircraft. And all this with some constraints, the constraint of being able to mix the older generation with the new generation in the systems, and to have a common interoperability between ground-based air defense and naval systems. This, as I said, program has been launched by France last month. Italy is in the process of joining it. And this is the end of my presentation. Thank you for your attention. I am ready to take one question.